Now, to get to 't Hooft and Susskind, um, so they were trying to understand this formula for the entropy of a black hole. And so let me again say the formula, it says that the entropy of the black hole, the number of degrees of freedom of the black hole, is equal to its surface area divided by 4 times Newton's constant. Okay. There are
Yeah.
various other constants there, like the speed of light and h bar and Boltzmann's constant, but we're adults here, so those are all one.
Yeah.
Um,
We'll choose our
so
units so they're one. So just so the audience is
work
clear
in
on
yeah,
what
we
that
work
means.
in units where they're one.
Yeah.
Yeah.
And so before you get to the formula
Yeah.
and how they think about it, it might be also useful if you agree. If we describe this puzzle that things fall into a black hole, it radiates, their information seems to be lost because the radiation seems not to carry the information regarding what fell in. But if you're looking at the black hole from far away, which after all is where you were measuring that radiation that came out, you
Yeah.
mentioned at infinity, just far away. Can you describe for us what you see when things fall into a black hole?
Yeah, well, um, really not well, so that I mean there for real black holes, that's a complicated question. There's an
Yeah,
accretion
sure.
disk, et cetera. Okay, but for an isolated black hole in the universe all by itself, um, the answer is you don't see too much. The object, say it's an astronaut, is falling towards the horizon. Um, and as they fall towards the horizon, um, they start to look dimmer and dimmer due to the gravitational redshift. And also, say the astronaut is holding a flashlight and pointing it at me just to make sure that I can see them. Um, I'll see the wavelength of the flashlight is getting stretched and stretched. The photons are getting lower and lower energy. And at some point, however good my eyes are or my telescope or whatever, I just can't really see them anymore. And that it happens, pretty fast actually. Well, I mean, it depends on the size of the black hole, of course, but roughly speaking, the time it takes for them to disappear is just roughly the time it takes light to go across the black hole.
Right.
Um, and then they've just become so dim that I can't see them anymore. And there's beyond that, I can never see them cross the horizon because well, I guess we haven't actually said what a horizon is, so we didn't talk too much about classical black holes, but it's the surface beyond which light can escape. And so once they cross the horizon, you can't see them at all. So you never see them cross the horizon. You just see them get dimmer and dimmer as they approach it, and then at some point you don't see anything.
And so have they crossed the horizon from your perspective?
Well, in some sense, no, right? Certainly you don't see them cross the horizon. I mean, that's this general issue of how do we define time in gravity? So in non-gravitational systems, there's a sort of preferred inertial set of reference frames where we can sort of roughly agree what time is. Um, but in gravity, I can draw time slices where they cross the horizon at some definite time. I can draw other time slices where they don't cross the horizon until infinite time. And both slices are just as good. So I don't
Right.
know. The only operational thing I can see is that I don't see them cross.
Right. Right.
Mm.
And so does that suggest a direction? I mean, if somehow their information is sort of hovering or smeared out around the horizon of a black hole, is that information there for the taking in some
Well,
sense?
you can try to say that, but then you need to, whatever theory you have that says that, you want to also be able to use that theory to describe the experience of the astronaut themselves.
Yes.
And from the point of view of the astronaut, they certainly cross the horizon. They have a watch and they cross it at 2:15 and on they go.
Yeah.
And they could be carrying an unstable atom and they want to know, did it decay before or after they cross the horizon? What's the probability of each? And they want to have some theory where you can compute that. And so a theory where you say they just never went in seems like a theory where it's hard to predict what they see once they do get in.
Right.
And I think that's an essential part of the story. That's something that was missed in the 1990s iteration of this, is that you haven't really solved this problem until you have a theory for the infalling observer too.
And so how then do the ideas of 't Hooft and Susskind begin to play with some of these concepts in an attempt to tell a narrative, a story, or maybe multiple stories that will ease the tension in this loss of information.
Right. So there are various ways into that, but I think the cleanest is to just go back to this formula for the entropy and try to think about, this formula. It says, you have a black hole, it's roughly speaking a black ball, and it has a surface. And they said that the number of degrees of freedom is equal to the area of the surface divided by 4 times Newton's constant. So it's a very large number, by the way. For example, the I think if you look at the black hole in the center of our galaxy, the entropy is something like 10 to the 95 or something. I don't remember exactly, but maybe 10 to the 90, I think.
Yeah,
It's
that's what, a 3 million, 4 million mass black hole, something of that sort of solar
Yeah,
mass.
yeah, that's right. And so for example, it's more than the entropy of the whole cosmic microwave background in the observable universe, just
Yeah.
just this one black hole in the center of our galaxy. So it's a ridiculously large entropy. Um, but the funny thing is that, somewhat paradoxically, is that Tuft and Susskind realized it's also a rather small entropy, if you think about it in a certain way. Because if you think about ordinary quantum systems that obey locality, like an oven or a gas, then the entropy is always extensive, which means that it scales with the volume of the system. So if you have an oven and you make the oven twice as big at the same temperature, then the entropy of the oven gets twice as big. Okay. And when I say twice as big, I mean you make the volume twice as big, not
Right.
the linear size twice as big. Um, Whereas with a black hole, it only scales like the area. And somehow with the oven, there's a very clear reason why the number of degrees of freedom goes with the volume. And it's what we were discussing before about the degrees of freedom here in my office and there where you are, right? Which is that in quantum field theory, at each point in space, there are independent degrees of freedom. And those are filling the volume of space. And so if you make the volume of space twice as big, you get twice as many degrees of freedom. And so the entropy gets twice as big. Um, so if you say that the entropy goes like the area of a region, you're saying that the number of degrees of freedom is actually less than what you would have expected from locality in quantum field theory. But if you think back to what I said before, that's potentially catastrophic because that means somehow the degrees of freedom here in my office can't really be independent from the degrees of freedom where you are. And if they aren't, then maybe we can communicate. Maybe if I do just the right measurement here in my office, I can send you a message without having to wait for the light travel time in between. And so Tuft and Susskind proposed to just run with this and say, really, you don't have these independent degrees of freedom at each point in space. All the degrees of freedom are just living on the horizon of the black hole. Okay. But then it gets really crazy because you can say, okay, well, we could be inside a really big black hole, right? And we wouldn't even know, right? The infalling shell hasn't reached us yet. It's going to reach us in 10 billion years. Could be true. There are certainly
Yep.
solutions of Einstein equation like that. And that would mean our degrees of freedom right here are really living out on some huge horizon surface out near spatial infinity. And the natural limit of that process is just that all the degrees of freedom of the system are always living off at spatial infinity. So we think we have all these independent degrees of freedom here and there and so on, um, but it's fake. Uh, and so what that means is that the very nature of space, where we think I have independent stuff that could be here, independent stuff that could be there, is emergent. It's not really correct. That the fundamental description of what's going on is you have this theory living off at spatial infinity. And it's only in certain situations and in some approximation that we can think that the degrees of freedom near me and near you are independent. Um, and you see, as soon as we say that, we're now getting hints of what the resolution to the paradox might be. Because if what's going on near the horizon where the Hawking radiation is being produced isn't really independent from deep inside, where the matter is that you collapse to form the black hole, then maybe there is a way for
Yeah.
the information to get out. Um, and so that's kind of the direction that things have gone in the last, say 30 years since these papers of 't Hooft and Susskind.
Right. So that's this holographic
Yeah, that's
idea.
this idea of the holographic principle, right? Right. So that was the term Lenny used for this idea that all the degrees of freedom live at the boundary. That's what happens in a hologram. You have a sort of two-dimensional image of a three-dimensional thing. And so Lenny proposed Lenny proposed the name, Lenny and 't Hooft proposed the idea that, really the way quantum gravity should work is you have this radical reduction in the number of degrees of freedom where the real theory is living at the boundary in this holographic sense.
And so this is a completely unfair and off-topic question, but maybe 30 seconds. Why would it be the case that we cognizant beings know about sort of this somewhat secondary or false picture of the emergent environment, and we aren't directly cognizant of the true degrees of freedom living out there on the boundary?
Well, that's the way emergence works, right? So, you know, this is far from the only example of something being emergent in
Yes,
physics. So, there's an example I like to use, right? So you can't really see it, but I have a table in front of me here.
sure.
And if I knock on the table, I think you can hear it.
Yep. I
Um,
hear some phonons.
yeah, you hear some phonons. That's right. So the information that I knocked here, and how hard I knocked is transmitted through the table by degrees of freedom called phonons. They're, lattice or compression vibrations inside of the table. Um, and there's a whole theory of phonons, that condensed matter physicists write down. There's even quantum field theory for phonons. Um, and when you want to answer the question, if I knock on the table here, when do you get a signal over there? Then you should use the phonon theory. Okay. And yet, the table is just some state in the standard model of particle physics with all, the quarks and leptons and everything. And in the standard model, Lagrangian, in the fundamental description of the standard model, there's no phonon field, there's no phonon particle. It's just some convenient fiction which you use when you want to answer questions about tables. And if you find yourself in a situation, a state, for example, where there is no table, then you're probably not going to talk about phonons. And so the idea is that space-time itself is like phonons. In certain situations, it's convenient to describe things using space-time, but there will be errors in that description that you can see if you do careful enough experiments. And in some situations, it'll just be a totally wrong picture of what's going on.
And for some evolutionary reason, we're aware of the emergent description, but not directly aware, unless you're really smart and do physics, of this more fundamental description.
Yeah, that's right. And I mean, and that's the way that physics has gone for hundreds of years, right? There's a lot of stuff that you and I know because we have PhDs,
Yeah.
which most people don't know because it doesn't seem very relevant for their daily lives, and that's fine, right? I'm not, of course, I'm not judging, right? That's totally reasonable, right? You should learn the things you need for your daily life first, and it's only when you ask these more refined questions, like, for example, how can we get through life without knowing quantum mechanics? We could have asked that, right?
Right.
Why don't we walk around thinking in quantum mechanics? And actually, quantum mechanics is essential for our daily lives, right? I mean, matter wouldn't be stable without quantum mechanics, right? You certainly couldn't have us without quantum mechanics.
Right.
But somehow there's an effective description called classical mechanics, which is pretty good in many situations. And you use it when it's good enough.
Yeah.
And when it's not good enough, then you need something better.
Yeah.
And
And thank
and
you.
it's our job to
Yeah.
find those situations where you need
Yeah.
something better.